So
Okay,
so going on.
So we have a focuser. That means we can move the camera relative to the primary mirror, just up and down. And yeah, focus is more or less constant. Of course, the stars are all very far away all the time, but because temperature changes and so the dimension of the telescope may change a little bit, we have to focus in between to get a perfect image. Perfect means that stars are as small as possible. So we have a telescope, of course. This telescope is currently connected to the software. It is not moving, it's parked. I can unpark it, and I will do it now. So nothing happens. If you have a look to the telescope, it does not move. But it's not, it is tracking. So the stars are moving over the sky. The Earth is rotating, and so the stars are moving, and the telescope is moving now also, but it's very slow, so we don't see it. And even if we would make an image now, we have a problem because the dome is not at the correct position. We can change that by saying to the dome that it should follow the telescope. And now the dome rotates, knows where the telescope is. It rotates and moves the slit so that the telescope can look through it. If I now move the telescope, the dome also will move. Just for convenience, I will switch on the infrared light of the camera. What's going on here? Was confused. So now we have some light, and we can see that the telescope is looking through the slit. No, sorry, wrong direction. Okay, so that looks right. And now let's say I will move I can move the telescope, just play around a little bit, and I will do it with this one. So I will move the telescope a little bit in one direction, and then the dome will follow. Okay, a bit more. And this is done by software, and the telescope is connected to the same software, controlling software than the dome. And if the telescope moves, the controlling software says the dome move in that direction. The controlling software knows the dimensions of the dome and the position of the telescope in the dome and all this. And so it can calculate how to rotate the dome so that the telescope is looking through it. Okay. I can park the telescope, and then you see it moves automatically. So this is the current situation outside. It's not completely dark. The telescope is looking through the slit. It's parked at the moment, and we can try to make some images just to get an idea of how to do that. first of all, we should switch the infrared light of the camera off, because otherwise this light of the camera will influence the images we do with the main camera. So switch it off. You see there is some light remaining from the sky, so it's not completely dark, but it is dark enough to get some images. So let us do an image just from where we are. Let's say 2 seconds. Normal image. Okay.
Actually, we have for the darkness, we have a list of objects from teachers and from me that we'll try later. Okay.
Yeah, later. Okay, so this is just an image. The resolution is much higher. It's reduced to 13% of the resolution, and this is what it is really. We are not in focus at the moment, but we can change that. But there's also an autofocus. But just let me change the filter. Okay, so we can move to any target. So which target would you propose at the moment?
Excuse me, sorry.
So we can move to a target. What target should we?
Yeah, we have, for example, M31, and near M31 there is M32 and 33, and we'll give some information about these targets. Let's start with Andromeda Galaxy, M31.
M31, yeah, it's you see here on the screen, the red frame is what the camera can see, and M31, the Andromeda Galaxy, is huge, so it even doesn't fit here. If you look through the Andromeda Galaxy, it's bigger than the full moon. So, but yeah, we can move there, and
let me give some information about M31 in order to prepare the observation. This is the Andromeda Galaxy. This is a barred spiral galaxy, which means that, as you can see at this image, there are some spires, and there is a bar near the bulge in the center of this galaxy. Is the nearest major galaxy, and it's the farthest object that we can see barely with a naked eye. Okay, it's in a distance of 2.3 million light years, which means that the emission of light needs 2.3 million years to catch our telescopes, our devices, our eyes. So it's very near, speaking about galactic distances. Okay. And has also a diameter of 152,000 light years. Okay, which means that if you travel with the speed of light, you'll need only 152,000 years to to catch the galaxy from the one side to the other. You can see it in real dark skies with the naked eye.
Okay, I moved the telescope to the target and I switch on the lamp so that you can see the movement. So now, where is it? We can do an image and hopefully you can see the Andromeda galaxy. Here it is. It's not very interesting because we need much longer exposure times to get more details, and we should do a focus first. But yeah, this is the Andromeda galaxy.
Believe it or not.
We can make a longer exposure, maybe then it's a bit more interesting. Let's say 10 seconds. You can see the time running here.
So right now we have the camera open for 10 seconds. That's
yes, but we should do an autofocus. We should do a focus first. Filter focus. Normally we do this by automatically, so I don't know how to do it by hand, but I can try. Hopefully it works. So now it will, the telescope will make some images. We'll look whether the stars are sharp or not and how it changes. And we'll try to get the best focus possible. So it makes some images, always changes the position of the focuser in between, and measures what's happening. And at the end, it will slew to the correct focus position, hopefully. Cannot see what's happening there at the moment, but the stars change in between. So it makes an image every few seconds and measures how big the stars are and how they change. And the diagram here shows the statistics of the image, how big the stars are and how it changes. This is the focuser position, so the position of the focuser for each image. And this is the statistics, the height is the diameter of the star. And you see it is moving out of focus. It will change the focus direction automatically in a few seconds. And so it will expand the curve on the other side. And then it will calculate the best fit and move the telescope there. Now it gets focus stars on the other side here.
Let's go near the M31.
Just a second. So now the focus curve was determined, and the telescope is moved to this point, which the software assumes is the perfect focus. And if you look through the, just a second, I have to put it here. And now it's much sharper than before. So the image looks better. So maybe M31 is not a very good destination. Maybe we can take another one.
Okay, let's go to the next one. Joseph, can you hear me? Oh, okay. So let's go. Yeah, to M32, which is a satellite galaxy to M31.
It's not GAM, just M. Oh, it's a little bit too early. The problem is you can see the curve, how high the target is above the horizon, and this target will be highest at about 9 o'clock in the evening. And if you have a look to the telescope,
it's pretty.
The telescope is looking east now. It is looking in a direction east, so where the stars rise. And you see, if I move the telescope more down, the telescope will hit the pillar, the lower pillar. You can prevent it by moving the telescope 180 degrees around and looking where the counterweights are at the moment. But yeah, I don't like to do that. But that means we cannot reach any star more than 2 hours before its highest position. At least if the telescope is on this side of the pier. And if you look here, position is 2012, so 612. Yeah, we will try.
Yeah.
We will try.
For teachers, think about that this diagram is identical to the diagram from airmass.org, for those who had a look at it.
So it seems to work. So this image you see now is from the internet. It's the same. So currently, the telescope is making an image of the target, and it measures the position out of the stars in the field and calculates whether the telescope is really there and where it should be. And M32, it's you see it. It's not exactly in the middle, but the software, yeah, can see that and remove the telescope so that it's in the middle. So if you do an image now, it is really centered. 10-second exposure of M32. Here it is.
Yeah.
So this is the Andromeda
galaxy.
you see some of the dark nebulas of Andromeda, of the Andromeda galaxy. I can talk a little bit longer and making a longer exposure during that time. What we normally do is not making a one shot and then we are ready, but we make a huge amount of shots, and every shot is 5 minutes. So let's say we have an exposure time of 5 hours, so we make about 65-minute exposures, and then on the PC we add them all together to reduce the noise and get more depth. So what we are doing now is not what we are doing normally. Normally, all is done automatically. So I write a sequence which targets should be photographed and where should the data be stored. And after that, we stack all the data together and get this high resolved deep images. So now we have 56 of 60 seconds, 58, 59. So now you see the contrast is much higher now because we did the 1 minute exposure. And if I move, this is a satellite galaxy, and I can now try to find some interesting stuff of M31, for example, here. This is a star cluster in M31. So what you see here are not stars of our Milky Way, but stars of a separate Milky Way, which is Andromeda, the Andromeda galaxy. So you can see single stars which are contained in a galaxy which is not our galaxy. And this is a special feature of Skinakas because the air is very continuous. There is no distortion or no big distortion of the images by the air because it's very stable. Yeah, that's very special for Skinakas.
Yeah, there are no mountains.
Yeah, the air is very. Yeah. So, but you see the lower part of Andromeda here and this small galaxy which is near to it. What else can we do? What do you want to see?
What else? Let's say, okay. NGC 147, which is another satellite galaxy.
NGC
147.
Okay. You can load an image. I'm just loading an image from the internet, so not from the telescope, but from the internet. It will load, and I can move the frame. So this is the galaxy, and I can move the part of the sky to match this. Oh yeah, we will do this. So we have not only one galaxy, but two. I can move it here and then say the telescope, go there, but I don't want to move it here, but I want to move it here.
Mm-hmm.
So I will slew and center it. So now the telescope is moving there. The dome is moving, we don't see it at the moment because now it's making an image, looking whether the position is correct. If not, it will remove the telescope to so that the position is correct. But the error was 8 arc seconds, so it is okay. So we can make an image. Let's say we start with 10 seconds. Oh, it's already there. With 10 seconds, just to get it. Okay, so here it is. Now, these are the two galaxies. And if you look at this image here and the image we did, you can observe that it's mirrored. So up and down is exchanged, but that's due to the way the camera is read out. And of course, in software, it's no problem to mirror it again. We can do it here also. Where is it? So now it looks right. But I'm used to this wrong looking stuff. I will make a 60-second exposure to get some more. And what you see here is the raw data. So this is the data exactly as it comes from the camera, with no software in between, just the photons which are collected in the camera and converted to electrons and counted are the result here. If you want more contrast, more color, and all this is done afterwards, after they expose all the exposures and offline with some imaging editors like Photoshop or something like that. But the real science data is included in these images. And of course, we cannot wait now for 1 hour to get a good image of this two galaxies, but this is what we normally do. We start an exposure, and then the target is imaged for 4 hours or even 10 hours, sometimes even more than 10 hours. And you see, the longer you make these images, the deeper you get. And you see all the noise here.
Yeah.
And of course, if you do longer exposures, the noise will be reduced because it simply averages out. And then you can see very small galaxies. Just an example, which we did is exactly this telescope. And of course, some color enhancements afterward. And this is not the real resolution of the image.
There's a whole image gallery at the Couple Observatory website, if you want.
So this is what we normally do. We make images,
Yeah.
and then edit them and put them to the website. And this is the real resolution of this thing. You see, there is, even here is some noise in the background, but there's not only noise, but also very small galaxies, which are very far away, which you can see in these images. You cannot only see them if you do a very long exposures. Some background galaxies, for example, this one here, it's a galaxy. It's not a star. Or here, there's a galaxy. And we have some images where the number of galaxies in the image are much higher than the number of stars in the image. It's not true for this one. But even here you see, here's a galaxy, here's a galaxy. All these very dim things are galaxies. Normally you can detect stars have spikes because they are point light sources. For us, they are point light sources. And galaxies are have more area, and so the light is not so concentrated like as in stars, and so they don't have spikes. So you can be sure this is a star because of the spikes, and this is not a star because of no spikes. Okay, this is only an example we did with the telescope. And yeah, a lot of things. If you are interested, just write down this web address, surf there, and we have hundreds and thousands of images. Most of them are done at Skinakas or partly in Namibia. And for example, M31, which after image editing and a lot of exposure time, this was exposed 12 hours, not 1 minute as we did, but 12 hours. But you see the star cluster we saw. Make it a little bit bigger, a little bit. This is a star cluster we already saw in this 1 minute exposure. Of course, it's much brighter here. And you have some other details in the image. Yeah. And that is the result of 12 hours of exposure and a lot of image editing. And then you get this kind of images.
As you can see in astronomy, you have to be very patient.
And this is when maybe we can take another target, which is not a galaxy but a planetary nebula.
In our targets, mainly I've chosen galaxies. Which planetary nebula is ideal for this time right now? Let me check it also. The Armstrong.
I don't know. Just, well, let's take another galaxy, huh? Or spiral galaxy, which is nicer.
Okay, another galaxy. It's quite near. These two galaxies. M110.
So, as before, I load the image from the internet. $110. Yeah, it's
Yeah.
now it's let's say I will have a look. Just a second. M74.
Yeah, also in
Yeah, it's more interesting because it's a spiral galaxy.
Yeah. Yeah, and it's a grand design.
Yeah,
galaxy.
It's not so big, so it easily fits into the field of view. But
it's like face on. You can see that. You can see its whole structure. These kind of galaxies, we call them grand design galaxies. When you can see all the spires.
No, it's too early. I have to stop that. Okay, it does appear flip, so we have to wait.
Yeah.
It should work. So now you can see what I'm trying to explain before. The telescope is moving on the other side of the pier because it's the target is simply too low. So it would hit the pier. Huh. So it knows it's not correct. It recenters the telescope, makes a new image. Okay.
Nikos, let me check your target. Okay. Because I have message.
Okay, I will start a 60-second exposure and go to the toilet in between. Sorry, just 1 minute.
Okay. Νίκο, μου έχει στείλει στο chat για το NGC 1300. Βλέπω ότι είναι πολύ χαμηλά το peak του. Δεν με ακούς? Okay. Είναι χαμηλά και το peak του είναι κοντά στις πάει αργά. Τις 11 και είναι κάτι παραπάνω από 30 μοίρες. Δύσκολο. Να δω για τον Ορίωνα λίγο. Ο Ορίωνας κάνει πικ είναι χαμηλά, γι' αυτό και δεν μου τα έβγαλε σαν προτινόμενα στο Air Mass. Τόνια, μας ακούς? Μου έγραψες ότι παρακολουθεί και όλο το τμήμα από το ΚΔΑΠ, σωστά?
Σας ακούμε, Παναγιώτη.
Καλησπέρα, καλησπέρα. Πόσα παιδιά είναι και...
Κύριε Παναγιώτη, υπήρχαν κι άλλα, όμως τώρα είμαστε 4 μες στην αίθουσα.
οκ.
Ήμασταν πολλά περισσότερα, αλλά επειδή πήρα χρόνο και από την ώρα της συναδέλφου, παρέμειναν αυτά που έχουν περισσότερο ενδιαφέρον και έχουν πάει τα υπόλοιπα παιδάκια στο άλλο τμήμα.
Ήμασταν 6 με 4.
Μάλιστα, μάλιστα.
Ευχαριστούμε πάρα πολύ. Δεν θα πούμε ευχαριστούμε στον κύριο Παναγιώτη.
Ευχαριστούμε, κύριε Παναγιώτη.
Να είστε καλά.
Ευχαριστούμε, κύριε Παναγιώτη.
Joseph, as you can see, we have some pupils in our company of really young age, early young age. Okay.
Okay. So this is the result of 60 seconds of the Spiral Galaxy. The reason that all is more or less yellow at the moment is because it's not completely dark, and we are looking above Heraklion, and all the street lights of Heraklion make the sky very yellowish. And because this is raw data, we don't have some contrast enhancement. But by the way, here's a small galaxy, a background galaxy of M74. I will show you M74, how it looks when it's
excuse me, dear teachers, express your feelings because you write me private messages. Express your feelings also to Joseph. They are impressed.
Okay, very impressive, the images that we saw before.
Okay. Yeah, it's a long way to get these images. You see the difference between this image, well, I will show you in the high result version. The difference between this image, which is, let's say, 5 hours of exposure, and this image, which is done with the same telescope, maybe even with the same camera, but it's not 5 hours of exposure, but it's raw data in only 5 minutes of exposure. But this, the galaxy is the same. For example, this background galaxy, we can find it. I hope we can find it by looking to this one. As I told you, it's mirrored, and I'm too stupid for this. Oh yeah, this I got it. You see this 3 stars, what, and these are, because it's mirrored, this dub, dub, dub. So if we follow this bow, we should see. We want to see this galaxy. Not so easy. So how can I mirror it the other way? I'm sorry, I'm not capable of doing this. Okay. So the galaxy should be here. Here it is. This one is this one. I think, I believe. I'm not sure, but yeah. You have to switch with your head. Yeah, but you can imagine if you do all this long exposure and contrast enhancement in Photoshop and so on, you get rid of all the noise, of course. And you get more color. And 5-minute exposure, which I started 4 minutes and 50 seconds ago, will end. And then we can see that in 5 minutes is much better than 1 minute. The problem is to get twice as many signal, you have to quadruple the exposure time. So this is the reason we have this very long exposure times to get very good quality images. But just look at the noise now, and just wait 15 seconds, and then the new image is loaded, and compare it with the noise of the new image, and you will see the differences. And only this. So, oops. Yeah. So it's not. It's interesting. What you see here is a bad image. The star was moving in this direction, was not stable. The telescope has to move to correct the rotation of the Earth, and it does it automatically. It does it very precise, but sometimes it doesn't work. And then it swings around the real position, and you can see it here. I can start it again. And this does not happen very often, but it happens. And especially if the telescope is on the wrong side, which it is now, it happens more. But what we always have is the problem that the rotation of the Earth is very precise. So you can correct this rotation and have the stars exactly at the same position. But because the stars are moving, or the light is moving through the atmosphere, and the atmosphere behaves different if the stars are very high above the horizon or very low above the horizon. The speed of the stars is not so constant as it should be, and you have to correct this atmospheric effects. You can calculate that, but it's not very precise because it depends on air pressure and temperature and all these different things. Or what you can also do is just measure the position of the star and correct some the false pointing. This is what we do. This is called guiding. We don't have only one camera, this main camera. We have a second camera. And while the big camera is making exposures, let's say 5 minutes, the small camera does exposures which are only 1 second. And it measures the position of a star every second, again and again and again. And if the star is moving, it says to the telescope, correct this movement. So that the star, this guide star, is always at the same position. And this is called guiding. And at the moment, we don't do guiding. But if we do real exposures, we do this guiding to guarantee that a star is at exactly the same pixel over hours. And you can do that only with guiding, because yeah, you cannot predict the atmosphere, how the stars are behaving when they are rising or setting, and so this is the reason we do guiding. I I did not started the guiding. I can do that. It's very easy. There's a second program which is running in the background. This one, and it just these are the stars seen by the other camera, and it makes an exposure every 10 seconds for 4 seconds or whatever, and keeps calculates the average position of all the stars and moves the telescope if you want that. I can start that when this exposure. No, I can start it now, maybe. So now, these are the stars which are detected. Here is the calculated virtual star, and the telescope is guided to this position now. Every now and then, it is guided. And then you get a curve here which shows the error of the star relative to the desired position. And this error is corrected every now and then you get perfect stars. And you have to wait some seconds to get more of the curve. So now we are guiding. It's very easy. When all the software is running, it's easy. Just make it apparently makes an image with a second camera, looks where the stars are, moves the telescope to correct the movement, and that's all. And what you see here are the errors the star has, how far away the star is from the perfect position. You see here the curve of the error. Red is for the x-axis, blue is for the y-axis. So the new image, half of the new image is guided, the other half is unguided. Normally, a 5-minute exposure is not so important to guide, but if you do many 5-minute exposures, then you should guide, because otherwise the image will move away. And this, what you see here is just an error in the friction drive. We have some sand or whatever influences the position, or the mirror flips. Maybe the next one is better. No, it is not. I don't know what's happening there.
Okay. Can you hear me?
Mm-hmm.
Okay. Let's see something else. NGC 7331 Caldwell 30.
So, NGC
Pegasus. NGC 7331. It's another spiral galaxy in 40 million light years. Okay. We'll catch an image of 40 million years ago.
Okay, this one is already above on the west side, so the highest position of this target is already reached. We are a little bit on the west side. So if we move to this target, we will see that the telescope is swinging back. You see the telescope is on the left side of the pier. And if I start Why doesn't it work? Ah, because I have to stop the exposure. I'm making the exposure, so I have to stop it. So now I can slew and send it. I will start the slewing and then switch to the. Now you see the telescope is dances back to the east side of the pier, because this target can be reached from the east side. Now, by the way, what you can see here below the mirror is the position where the camera is when we use a secondary focus. Currently, we use the primary, and this is here. The camera is positioned here. The dome tries to get the position correct, but because the telescope is moving, the dome moves here and there and all the time. Okay, so now it does an image. I think the position will be not correct because the telescope flipped. Oh yeah, it won't work. So now the galaxy is centered. It's not centered. The telescope is recentering. So now we are in the center. Here it is. So let's say we make a 60 seconds exposure. We can start guiding.
Of course, if there are any questions, you can tell us anything. Okay.
Yeah, if there are any questions, just ask. So I started the exposure of this galaxy. This is how it looks after 2 seconds. With this big telescope, of course, if you have a bigger telescope, you will see more in this short time. But we only have a 60 centimeter. A 6-meter telescope will be not 10 times faster, but 100 times faster. Of course, it's a square of the radius, the area. So if you have a telescope with 10 times the diameter, we will have 100 times the area. And that means 100 times more photons during the same time. Of course, this is much more. Normally, these very big telescopes are not used to make images of a galaxy. You don't need this huge telescopes to make just an image, but they measure the color of these galaxies. So they make spectra, and that means that the color which falls through the telescope is split to the different wavelength. And that means you even need much more light because it is split to the different colors. And then you need really big telescopes to get enough light to have a signal which is not only noise. So this is a 2-minute exposure, hopefully. Yep. And you see you see much more after 2 minutes of this galaxy. It's a nice galaxy. It's not very big, but you see there are a lot of galaxies nearby. This is the main galaxy, and you see all these galaxies here. And since guiding is working, let's say we make a 300 seconds exposure. And during this 5 minutes, just ask questions. What you want to know, just tell me.
Yeah. Wake up.
Can you explain us how we can measure the distance from this galaxy from the Earth?
Yeah.
How we can estimate that the distance is about 40 million light years?
Yeah. Okay. Measuring distances in the universe is a interesting theme. There are different ways to measure distances, and they depend on how far away the targets are. Let's say the planets in our solar system. It's more or less easy to measure the distance because you can just wait half a year, and then you know that you are on the opposite side of the sun, and you can just measure the angle between the Earth and this planet, and it's just a sort of triangulation. And that also works for stars which are not too far away. So very near stars, let's say Alpha Centauri or so, which are only a few light years away, you can measure the position now and half a year later, and then the position changes relatively to the stars which are much farther away. So you make an image, wait half a year, make the second image, and you will see that stars which are very near move relative to the stars which are far away. It's a parallax, you know, this parallax effect. Like you look, you see different images if you look with the left and with your right eye. And it's the same if you have a telescope. Then the right eye is now, and the left eye is half a year later. And then it's only a way of trigonometry. So, and this is how stars, which are not too far away, are measured, the distance of stars. And so you know how far away they are. And some of these stars change their brightness because they are variable stars. They do it because the physics of the star is so. It's and the brightness change is depends on the sort of stars, and you can measure the sort of stars by getting the color of the star. And when you know, okay, this kind of star, we have this kind of star, and it changes brightness between this and that, and if it would be our sun, it would change brightness from here to there. You can calculate how far away these variable stars are. And that also works if they are in, let's say, the Andromeda galaxy. And so you can measure the distance of stars which are more far away. than the stars which you can get with the parallax. So you get the parallax measurement for stars, and get the measurements of them to compare it with stars which are more far away and get the distance from of them. And what you also can do is you can measure the color of the star if you know what kind of star you have. Let's say you have this variable star and you have the color of the star, and this color may be redshifted because the star is moving. This redshift, it's like the tone of cars which are coming towards you or are leaving you, and the tone gets higher or lower. And that's the same for stars which are moving away from us. They get redder because the waves, the light waves are here, are stretched. And so if you see a star which should have this color, because of its physics, because of its behavior, for example, it's blinking, and it doesn't have this color, but it has a color which is more red, it is moving. It's moving away. And the speed of moving away depends on how far away the star in a galaxy is. It's because the universe expands, that stars which are stars or things which are very far away move faster than things which are not so far away. So depending on the color of these galaxies or the stars, both, the speed of movement of them away from us, and that is directly proportional to the distance of this galaxies or stars. And we know this proportional factor, and so we can calculate how far the galaxies are or the stars are away depending on their color or their redshift. But it's interesting, it's called Hubble constant, because Hubble was the first who detected this behavior of stars or galaxies which move away. And this Hubble constant is, it is constant, but the people are not sure how big this constant is. It depends on how you measure, and you get different values of the Hubble constant. But yeah, that's a way to calculate or measure the distance. Just look at the colors and look how these colors are redshifted, so you can calculate how far away they are. Okay.
Thank you very much.
Other questions?
Δέχεστε ερωτήσεις από τα παιδιά?
We can translate them.
Okay.
She talks about questions from really young pupils. And also, excuse me, Tonya, there is a question in English at the chat.
Ωραία.
Why do the images have a yellow-green tint? Is it just a filter used that determines this? We talked about before, it's about the noise. Okay. You can tell us something more.
Different effects. You have, first of all, you have the air glow, or the fact that the sky is not black, completely black, is mainly because we are looking towards Heraklion, and it's all the lamps of Heraklion just bring up the lights. But what we see here is only a preview, and the color which we see here is not very good edited. I can save this image and make the colors more brilliant. This is only a raw image. You see, it's right here and it's yellow there, but that does not mean that this is a real color, because it's just a raw image. If you ever looked to a normal photo camera and look to the raw images of a photo camera, not the JPEG images you make with your phone, but the raw data, it will look more or less the same than this. The color enhancement is done in post-processing, and it's not done here. And so the color is more or less yellow white, and all the blue and high contrast things you won't see. If you look with your naked eye to the sky, you don't see, even with the bright stars, you don't see extreme colors. You see the bright stars, which you can see in color, let's say Betelgeuse or Vega and Aldebaran. These are stars which have different colors. Aldebaran is a yellowish, has a yellowish color, and Vega has a white color. But you must train your eyes to see that. Normally, they look more or less white. And this is what you see on this raw data. To get the real or the impression of real color, you have to enhance its color. For example, this one is yellow. This star is yellow, and this one is more blue. You can see it, but it's not very obvious. And to get it more obvious, you have to turn the knobs of color saturation in post-processing to get it more obvious. The differences are not very big. If you look to the raw data of these images, yeah, they are not so interesting. To get them more interesting, you just have to turn the knobs. Okay?
Believe that we are okay. So, Tonya, tell us the questions of students.
Γεια σας, είμαι ο Νικόλας.
Γεια σου, Νικόλα.
Και θα κάνω αυτή την ερώτηση. Τελειώνει το διάστημα. Άμα τελειώνει, τι υπάρχει όταν τελειώσει?
Αν τελειώνει το σύμπαν. Δηλαδή.
Ναι.
So, Nicholas asked for if the universe is ending somewhere. Okay. As we know until now, we talk about the birth of the universe. I'll talk it also in Greek. Okay, Tonya. We'll talk about the birth of the universe, approximately 13.8 billion years before. With this kind of birth, we had also the birth of the space. Okay, so the Big Bang, as we call it, is not something that was happened somewhere. Okay, it was the birth of the space. So, if we have the birth of the universe, generally, there is a size of the universe. We talk about the size of the universe, but not in a way that actually can understand it in a very basic level. Okay. If I remember right, we talk about a radius of 90 billion light years, the radius of the diameter. Josef, you can correct me on this, of course.
Yeah. So there are, what is the size? Is the size where you can get if you have a very, very fast rocket, or is the size where it ends? Or how can you detect where it ends when you never can reach it? Definitely cannot reach it. So the universe, which we can see now, we can see the light had only some time to come to us, and this time is the age of the universe. We don't know exactly the size of the universe, but we know exactly the age of the universe, and the age is about 13 billion years. And so the light has about 13 billion years to travel. So things which are more far away than the light has time to get to us, we cannot see. And we will not see it ever, because these things are moving away from us. And they're moving away very fast. So even if we want to go there, we try to go there, we will never reach them, because they are moving so fast that we cannot reach the speed. So even if
there
there
is
is
misconception about the age of the universe and the size, about
even if there is a size, we will never reach the edge, and it gets bigger and bigger. And it's like, by the way, the universe and old men have something in common. They expand. So and we know that the expansion of the universe is getting faster. So it is not constant. It's not growing at a constant speed, but the speed is getting faster and faster and faster. And the end of the universe may be that all is so far away from each other that nothing will see anything else.
So, in Greek, ο Josef ουσιαστικά μας επεσήμανε και το εξής, το οποίο πολλοί έτσι άνθρωποι είναι λογικό λίγο να το μπερδεύουμε. Μιλάμε για την ηλικία του σύμπαντος και λέμε ότι είναι περίπου 13,7-8 δισεκατομμύρια χρόνια. Οπότε τους πιο μακρινούς γαλαξίες που μπορούμε να δούμε είναι μέχρι αποστάσεις 13,7 δισεκατομμυρίων ετών φωτός. Για το μικρό μας φίλο να πούμε ότι το ένα έτος φωτός είναι η απόσταση που κάνει το φως σε ένα χρόνο. Οπότε μπορώ να δω αντικείμενα που είναι 13,7 δισεκατομμύρια έτη φωτός μακριά μας. Δηλαδή που πιο απλά να το πούμε, το φως τους χρειάζεται 13,7 δισεκατομμύρια χρόνια για να έρθει σε εμάς. Δηλαδή χρειάστηκε το φως τόσο χρόνο όσο είναι η ηλικία του σύμπαντος. Αλλά το σύμπαν διαστέλλεται και διαστέλλεται και πολύ πιο διαστέλλεται επιταχυνόμενο, όλο και ανεβαίνει η ταχύτητα διαστολής, να το πούμε πιο απλά. Οπότε υπάρχει και κομμάτι του σύμπαντος το οποίο δεν μπορούμε να το παρατηρήσουμε. Είναι πολύ πιο μακριά, οπότε δεν έχει προλάβει το φως να έρθει σε εμάς. Ο χρόνος δηλαδή που χρειάζεται και είναι μεγαλύτερος από την ίδια την ηλικία του σύμπαντος. Οπότε εμείς δεν μπορούμε να το δούμε. Το καταλάβαμε?
Του μετέφραζα ήδη όση ώρα.
Ωραία, ναι.
Και έχει μείνει με το στόμα ανοιχτό.
Η ερώτηση είναι πάρα πολύ καλή και είναι εξαιρετικά δύσκολες αυτές οι έννοιες. Γενικότερα. Δηλαδή...
Θέλεις να πεις κάτι στον κύριο Παναγιώτη?
Ναι.
Τι?
Ευχαριστώ πολύ.
Ευχαριστώ πολύ. Σας ευχαριστούμε πάρα πολύ.
Να είσαι καλά, Νικόλα. Θα δούμε, έχουμε λίγους στόχους ακόμα. Κάτι άλλο που θέλουμε να πούμε, να ρωτήσουμε?
Sorry, I drank too much coffee. Okay. So now you can see the guiding here, the differences between the correct position and the position which is measured. Now it's running a few minutes longer. You see the curves here, and you see the distance from the optimal position, and it's less than 1 arcsecond, much less. An arcsecond, how much is an arcsecond? Let's say you are at Crete and you are looking at Rome.
Yeah.
There's a bottle of Coke at Rome. And if you look at the top of the Coke and the bottom of the Coke, this is about 1 arcsecond. This is a resolution we have with this telescope. It's very high resolution, and this is the correct, or this is the error we have, less than 1 arcsecond.
I steal your example, okay?
Yeah, the problem is the example is not correct because you have to say that this bottle of Coke, where you can measure the top and the bottom, it's moving with 300 kilometers per hour, because the stars are moving over the sky. So you have to look to the Coke while it is moving in a very fast car. And that is what we are doing. And that's because that is why we need so much technical details to get the correct things, the correct data. And if it works all, it's done automatically. You can just press a button and get the data 5 hours later. But getting to the point that all works as you want, that's the real work. Here you can see the distribution of the telescope, where it is pointing in comparison to where it should point. The destination is exactly in the center of the circles, and these blue dots are where the telescope is actually pointing. And you see, this is 1 arc second. That is 1 bottle at Rome. So this is half a bottle, and that is a quarter of a bottle, a Coke bottle seen from Skinakas in Rome. So it's very exact. And
Nice
of course,
example.
if it's windy, let's say it's a little bit windy, the telescope is shaken by the wind, and then you will see that the pointing diagram here will look completely different. It's the cloud is much bigger because the telescope shakes only a very small amount, but of course you can see that, and you will see that.
Josef, tell us the upper limit for the speed of wind for 60-centimeter telescope.
It depends on the direction.
Yeah,
and when the dome has the slit, and if you look not into the wind but away from the wind, it's, well, let's say 20 kilometers per hour are okay. 30 is not good, but it's acceptable. 40 kilometers is definitely too much. The amount of power in the wind is not linear with the wind speed. If you have twice the speed of wind, the energy stored in it is, I think, 8 times the amount. So there is a very sharp edge from usable to not usable, and it's about 30 kilometers an hour. If you are not looking through the into the wind, if you are looking in the wind, even 20 kilometers is too much.
Yeah. I remember from the summer that with the biggest telescope, the limits were higher, really higher.
Yeah,
much higher.
Yeah, it's bigger. The dome is bigger. It's heavier, and if you have a heavy mass, it is not so much. And the problem we have with the telescope is that the way it is mounted to the ground is not very optimal, and it is what it is. You can, if you step on the place where the telescope is mounted, you can see that the stars are moving only from your weight, because the telescope is twisted a little bit, or the place where you stand on is twisted by your weight. Yeah, but it is what it is.
Yeah, of course. So,
any more questions? I cannot read Greek, so you have to translate that.
Yeah. The last comment is by a teacher who leaving us because she had to leave. Okay. So let's go to another one.
Is it possible to see some kind of nebula?
Let's see.
Yeah, you may diffuse nebula like
planetary or general.
Let's see just a second. We have to find one which is reachable now. I think this one should be reachable.
So it's Cocoon.
Doesn't find it. Okay. Maybe this program does not know all this. Okay. Yeah, I started a 50-minute exposure, 30 minutes. If we wait 1.5 minutes, we can see this 50-minute exposure. I think we should do that. And then we move to the Cocoon handler. But just to see how this target looks, not after 5 minutes, but after 50 minutes. And just wait 1 minute and we are ready.
I wanted to ask, like, how exactly far can we see from the modern telescopes that Earth has and the modern telescopes in space, such as James Webb telescope?
You mean we in comparison to them or they?
Generally, how far can we see from the biggest telescopes?
Yeah, of course, it depends on what we are looking for. If you, let's say, very bright galaxies, which are, yeah, they have some special cases, you can see about 13 billion light years, so 500 million light years old galaxies. So if the universe is 13.5 billion years old, you can see 13 billion light years away. So 500 million light years missing to the edge. And this is James Webb, and all the galaxies and what you see, they are redshifted so much that they are only emit infrared light. So here's the 50-minute exposure. You see it gets brighter and brighter. You get less noise. You see all these galaxies get more detailed. This is a 50-minute exposure. And you see, especially in this image, there are a lot of galaxies, background galaxies. Not only the big ones, but also a lot of small ones. This one, for example, is a nice one. Okay, so the other target, this one, we move there. It is.
Joseph, excuse me, we have a question about Jupiter. I suppose that the current focal length is not for
Yeah.
Jupiter.
So if you look to this image and imagine the moon, the full moon fits on this image. The image is, yeah, the moon will have this size. And Jupiter, it is a big planet. It's the biggest planet we have. But even Jupiter is so small that you won't see very much detail, more or less no detail with this telescope, because the resolution is, or the focal length is not big enough. You need bigger focal lengths. And at the moment, Jupiter is not high enough, so we cannot make any images of Jupiter. Normally, if you want to make images of planets, you have very specialized equipment to do that. This is a telescope with a very long focal length, at least 10 meters, not 1.8 meter we have, but at least 10 meters. You can add some special lenses to get the focal length, which is longer than your telescope. And you don't need these extremely long exposures, but very short exposures. Jupiter is bright, so you can do it with a 50s or a tenth of a second or whatever, and then you make a lot of images and just wait until you get a very sharp one. And this is depending on the atmosphere, how the atmosphere is working, how the flickering of the atmosphere is working, and so on. And so the telescope we have and the camera we have is not very well suited for planetary imaging, as it is now. We can switch cameras, and we can switch lenses and the configuration, and then you get images. Just a second. This is done with the telescope. It's done during one night, and you see the moons of Jupiter moving in front of Jupiter, and you see the shadows of Jupiter there. But even then, this was a very special equipment, and even then, the moon, the Jupiter is not very big. Do we have? This is Mars. I think most of the planetary images you know are from satellites, which have moved there. So the planets are very small, and they are so far away that you don't get any details. This one is very good. They are very good images of Mars, but even they don't look very astonishing, because you know all the images which are done by special satellites, which are moving through the solar system and making images of these planets when they are very near to them. From Earth, you won't get images which are much sharper than this, because the atmosphere is disturbing your images. So it is not possible. And getting these images, you need some very special cameras. This is done with a telescope, but in secondary focus. And there was a video camera, not a normal camera, but just a video camera, because it makes a lot of images very fast, one after the other, and you can just take the best, sharpest ones and add them all together. Okay. So we are waiting. Just some minutes for the Cuckoo Nebula. You see it's not so obvious here, because it's only a 2-second exposure. You see it is red. It gets red. But if these 5 minutes are gone, we will see it much clearer. Any other questions?
Another one is, can we consider the expansion of the universe faster than the speed of light?
Yeah, the universe is not moving, it is expanding, it is getting bigger. So the objects are not moving one to the other, but they are...
yeah, the space between...
Space is getting bigger. The space is getting bigger, so yeah. this could be faster than the speed of light, because the different objects in the universe are not moving, but
it's not a single thing that actually moves. It's the entire space among them that that expands.
It's a different the position or the relative speed between these objects may not change. Maybe zero. So there is this object and that object, the speed between them is zero. But because the universe expands, the distance changes. Without speed, distance change. It's not obvious, but yeah, it's true.
And it's not something that is stable as a rate of expansion in all the ages of the universe and the old distances. Okay, it's not so. The answer to this question is not so simple, actually.
So we have 5 seconds for the 5-minute exposure of the Cocoon Nebula. 2, 1, and here it is. So someone asked for a nebula, and this is more colorful. Yeah, you have this red light, which is H-alpha emission. So there's gas, hydrogen, and it is ionized, and so it is glowing from itself. It's not lit by stars, but the gas itself is glowing like a neon lamp or whatever. And this hydrogen is glowing in red. It's a very special color. It's always red. By the way, here, if you look here, you see some white nebula. And this is not glowing by itself, but this star is working like a torch, shining through the dust which is there, and so you can see the dust. There are a lot of dust in this image. Maybe you see here where the stars are not so dense. This is not because there are no stars there, but there is dust in front of the stars, and the light cannot come through the dust. And that is the reason you don't see stars here. But if there's a bright star near this dust, it is capable of bringing light to the dust, and you see the dust like a car in nebula in fog. If the car is spotting with its light to the fog, you can see the fog. So this is the Cocoon Nebula, and we did it. It's not long ago that we did the Cocoon Nebula, and I just show you the result. This is more or less the same.
What is the distance of this nebula?
Pardon? What is what?
What is the distance? The distance, how far is this nebula?
Oh, don't know. I think it's not very far away, maybe a few thousand light years. It's in our galaxy, and it's not too far away because it's big. And things which are big are normally, our galaxy which are big are normally near. And you see
4,000 light years, actually.
Yeah, maybe, yeah. So you see, this is a result after, I think, now you can see the dust, and you can see the reflection of the star here in the dust. And the main difference between this and the image is this is nearly 20 hours of exposures. So a few nights, all the night exposed only this destination. And what you see here is only 5 minutes. But even 5 minutes, okay, this one is very bright, so you can make it easily. So hope you are okay with this diffuse nebula.
Yeah, really, really nice.
And this is the remaining of the explosion of a star.
No. It's what you mean are planetary nebulas. They look different. This one is just a cloud of gas and dust, and that is lit by stars, and the gas or the hydrogen is glowing by itself. It's not a planetary nebula, not an exploded star, vice versa. All the mass in this area, all the dust may contract, getting more dense and more dense, and then start a new star. So it's not that a star is exploded there, but it may happen that a star is born there. And maybe all the stars, I don't know, but maybe all the stars here are born due to the dust which is here. You see this one here? I will show you in the enhanced version. Where is it? Here. I'm not sure, but maybe you see there is the dust is gone here, and there is a star. Maybe this star was formed from the dust, and then when it started emitting light, it blows away the remainder of the dust, and this is the reason of this free places there. So again,
we see the formation of a star over there.
It may be. I'm not sure, but it may be. Yeah. For example, just let me show another one where it is well known that it's true. You know, most of you know this is the Eagle Nebula, and there are stars at the top of these globules, and they are born in this dense dust areas. There are new stars born here. Or another one is here. This one is sharper. You can see here stars which are born in the region of the densest clouds here. So in contrast to this are these exploded stars, a reminder of stars. I think the most famous is M57, the Ring Nebula. There's a blue star. It's a reminder of a very big star which exploded and throw out all the material except the very inner core, and this inner core imploded and gets a blue or a star or white dwarf or whatever, and this is a star which died, not a star which was born. They are called planetary nebulas, not because they have something to do with planets, but only because telescopes of older telescopes of former times were not able to resolve them, and they looked a little bit like planets, and so they are called planetary nebula, but they don't have to do anything with planets. It's only their name. And a lot of different shapes of this planetary nebula, just exploded stars. This one, I think it's the biggest one. Most of the time in the center there's a star, and that is the reminder of this explosion. You can see how this the rest of the former star moves outwards. Okay, so where are we here? I don't know the PN we can make now. I can try. Just I give it a try. Frame.
Yorgo, NGC 1499 is really low. I don't know the C20 object, actually.
No, 20 degrees. You can try it. Okay. It's very low, but we will do the
Which of them? Which of them? Is it
so.
NGC 1499? Which one?
So here's the ring nebula. We can try to make it. There's a galaxy nearby. We can try to make it. It's funny. Slow and center. Hope it works. Okay. It is.
Nice.
So it's a very bright object, and you see the different colors. Let's say we'll make a 60-second exposure here. What's going on? It's not done with the centering. Well, you see the central star even here. And by the way, this is a galaxy, the background galaxy here. You see the central star, and that was a 2-second exposure. It's very bright. If you see, it's interesting. If you see this with your naked eye, it's easy through a telescope, of course. You won't see the colors. With your naked eye, even through a telescope, you won't see colors at all, except very special targets. They must be very bright, and this extremely bright targets are extremely rare. 57 is very bright, but it's not bright enough to see colors with a normal telescope. The reason you cannot see colors is, in German we say nachts sind alle Katzen grau. So at night all cats are gray. Your night vision is not a color vision. You can only see black and white or intensities during the night, not colors. Don't know how to change the color here, but you see it's saturated. It's so bright that all the colors get white here. I don't know how to change that. Okay. It's not very clear now, but it's the stretching is switched off now, and you see only the very bright parts of the image, and you see the nebula here. I'll switch it on again. It's just too bright, but you can see the galaxy here. Okay, so this is an exploded star. The other one was just a diffused nebula.
Yeah.
Okay, other
it's very-
questions?
At its very end. Okay. Let's have a final try for NGC 7000, a last target. Maybe it's in an altitude of 60 degrees.
And you see what?
NGC 7000. It's in North America.
Okay, it's very deep. Yeah, we can. Yeah, it's a very big target.
Yeah, it has a really big field.
Yeah, it's very big.
Yeah.
So moving here is, let's say we want to see this one here. Okay, you can see this pillar then. Okay, so the telescope. Just a look. What is going on there? Telescope is moving. Okay. This is also very bright. So the arrow was too big, makes it new.
Can I make a question?
Yeah, of course.
How often do you have to calibrate the telescope?
What do you mean with calibrate? There's an optical calibration or a pointing calibration or
I mean, how the telescope knows how to turn to find the objects. When you said the telescope find the NTC 7000.
Yeah.
How easy? Not how easy? You have to make some calibration just to target the image.
Yeah.
Is it so?
It does it by itself. It does it every time. So, for example, it did it now. It moved to the target and it made an image, and then it's called plate solving. It solved the image and compared it to an atlas of stars, which is in the internet, and it measures the difference, and then it calculates. Okay, the telescope should point here, but it's pointing there, and the difference. Do the calibration by yourself, and so every image or every target it moves to the target, makes an image, measures the position, and corrects the position. So it is correct afterwards, but it takes 2 attempts. It is gone now. Don't know whether I can. Where is it? Is it? Plate solving. Yeah, it's called plate solving. Makes an image, compares the image with data from the internet, gets the difference, and then it knows exactly where it is, and so it can say, okay, this position is here now. And then if the position is absolutely correct, it makes some smaller movements to get to the target where it really is. So this sort of calibration is not needed very often because it's done completely automatically. There are some other calibrations, for example, optical calibrations, the mirror tilt and the lens tilt and the camera tilt and all this stuff, which is mechanical calibration. This is, must be done, let's say, maybe 2 or 3 months. Okay, here's the North American nebula. And let's take a 60-second image of it. Yeah, astronomers normally wait. No, by the way, most of astronomers think that they are looking through telescopes. I think looking through a telescope is not the way people use telescopes nowadays. You can do that. You see some stars, but what we can see with the big telescope and the camera is much more than with your naked eyes, because this cameras can make very long exposures and gather all the photons over a long period of time. And what you see with your naked eyes is just a moment. And so you won't see, even with the big telescope, you won't see very much. And astronomers don't look to the stars, they make photos or spectra. So here's the part of the North American nebula. You see these globules, the globules here, some dust here. Here's, it's interesting, here's a star in the dust, which is so bright that the light of the star is reflected from the dust. Yeah. And this image is done at this moment at Skinakas, 3,000 kilometers away from me, and I did it. And this is what I like. It works, and you see something which is not usual to see. And getting it to work 3,000 kilometers away, or in Namibia it's 10,000 kilometers away, I like that.
Yeah, it's really astonishing.
Okay.
Josef, you can collect all this raw data, and we'll discuss later about what we can do with raw data, and how can I share to the teachers. We'll see it later. So, any final questions? I believe that we saw many things. Josef, if you want to add something at the end. Did you enjoy it?
You mean me or?
Yeah, you.
Yeah, of course, I explaining things, I like it. If it works. If what I don't like is to explain something and then something happens. For example, someone is walking into the dome.
Yeah.
That
We really informed that we have the.
But yeah, but all the other stuff worked. So
yeah,
you get a virtual, not virtual. It's a real tour through the sky. It's a real telescope getting real photons, and you see it in real time. Yeah, I like it.
Okay, we have.